Meredith.
I'm missing $20 that I... Okay. Yeah, I get kind of depressed if no one interrupts because I do talk to myself, but it's usually not about seismology. So it's more like if I water the plant or whatever. So it would be good if you interrupt. Also, these are kind of, I'm relying on you for discussion because I'm kind of a Luddite, and so I don't have like dancing beer bottles and stuff like that. So, okay. All right, so I'm supposed to talk about the seismic structure of the continents / Earth and try and take advantage of the basic concepts that Yaron just explained before the coffee break. And he actually showed you the 1D structure of the Earth. So I'm not going to go over that. Instead, I'm going to try and focus more on the continents and how the continents are different from the rest of the Earth. And we can just kind of focus the details of that depending on where the discussion goes, hopefully. So I have to say that I'm kind of a long wavelength seismologist. So when I saw this about talking about the structure of the continents, I thought, oh, okay, great. So mantle variations and this and that. And oh, right. But, okay, then there's also the crust. So for me, the mantle is kind of, the continent means the mantle, but actually the crust is important too. So I'm actually going to start with the crustal structure and kind of try and approach it from how we see the crust, or what we know about the crust from seismology on the sort of the global scale, the large scale, as opposed to looking at what do we know about the crust by focusing on one particular part of the crust or one continent. Can you guys hear me? Okay, so when we're talking about seismic constraints on crustal structure, one of the main things that we're actually talking about is making use of these kinds of regionally traveling seismic waves and travel time curves that Yaron showed you, the ones that do something interesting in the crust there. And so we try and take a whole bunch of these curves recorded regionally or locally and interpret them in terms of the crustal structure. And a lot of what we know about the continental crust from this type of work has been compiled to try and give us a view of what the continents look like overall. And this is work that Walter Mooney has done a lot of, and then with various seismic collaborators, including Guy Masters and Gabi Leski. So this is a compiled data set from the crust 5.1 model, which was a 5 by 5 degree crustal model, from Mooney et al. In 1998. And the data set hasn't really changed a lot since then. What's plotted here are the locations, the midpoints of seismic refraction profiles. So that means places where someone went out and basically set off an artificial earthquake over here and recorded it over here, got the travel time curve, and then interpreted it in terms of the Earth structure. So those have been done in a lot of places on the Earth, as you can see, all of these dots and triangles, but not everywhere. Okay, so we have a lot of coverage in the places you sort of might expect, not so great coverage in other parts of the Earth. But those are the data that are there. And just to remind you what those look like, those profiles generate a lot of seismograms arranged here vertically, and someone's gone and picked the first arrivals of those, these are mostly P waves, and made a travel time curve with the famous triplications, and interpreted that in terms of the crustal structure in that location. And so you do this at all those triangles across the surface of the Earth, and you end up with a whole bunch of seismic velocity profiles. So here are a bunch of those P-wave velocity profiles made in different parts of, in this case, the western US. And so you get your P-wave velocity profile. You also get a crustal thickness. Find the discontinuity where you go to mantle velocities, and so on. So we have this for all of those different triangles. And we can look at some characteristics of what the crust looks like overall. Okay? So if we do that, for example, for crustal thickness, instead of, say, velocity or something, these are, I thought we should have some histograms in seismology, too. Here's for shields, platforms, regions of extended crust, origins. You can do this for more types. Crustal thickness here, and just the number of observations on the y-axis. And so this is 40 kilometers right here. The range is from 20 to 80 on these plots. And you can see that there's a pretty wide range of values, even within one crustal type. But hopefully you can also see that there are some differences between the types. Extended crust, perhaps not so strangely given that it's been extended, has a smaller crustal thickness than, say, the shields, around 30 kilometers here, around 40 kilometers there. But again, a pretty wide range of values within each of those regions. Okay. But the main point is really that, okay, you can go and you can measure this, and you can do it at all of these places, and you've got your profiles, your crustal thicknesses, and so on. I should mention that when you're doing that, you're mostly measuring P wave velocity. Maybe something like 10% of these maybe have a constraint on the S wave velocity directly. But it's mostly P wave velocities, and you get your profiles and your crustal thickness. Okay, so that tells us something about what the crust looks like in those particular places. And actually, we'd also like to know what the crust might look like in Western Africa, or in South America, or in Antarctica, or in Greenland, where there are no dots. So how do we do that? Well, the approach that these authors took is a little bit like when Roberta says, I want to know what is the composition of the crust on the planet, and you have observations in as many places as you can get them, but that doesn't tell you what the average answer is, or what the answer is over somewhere where you don't have an observation. So what they do is they take the samples that they've got, and then you actually use geology, even though you're a seismologist, and some statistics, nothing complicated, to figure out how to assign information about the crust to areas where you don't have observations. So what's been done here is to take a map of the world. In this case, it's divided into 5-degree by 5-degree squares. And you use geological maps, other information, to assign to each of those 5 by 5-degree blocks some kind of crustal type. So you say, well, all right, this is the ocean. That's pretty easy. And then you say, all right, okay, up here, this red stuff is cratons and shields, Archean platform areas. Then you have over here, I guess all the red colors look kind of too similar, but extended crust. You've got some shelf transition regions, and so on. You basically go and try and identify as nearly as you can. It's never going to be perfect because no geology is constant over 500 kilometers by 500 kilometers, but you do the best you can with that. And you say, all right, then I can take all the observations I have where those triangles are, and I know what kind of geology they have. So then let me go over here where I've got the geology, but I have no refraction profile, and assign a similar type of seismic velocity structure over there. Does that make sense? Okay. It's a lot of work, right? So it's a very, very useful endeavor. Okay, so if you do that, then what does the world end up looking like? Well, here's an example for what the crustal thickness looks like. This is actually for a model Crust 2.0, a 2x2 degree model that's built in the same way. It builds on the Crust 5.1 model, but uses a finer parameterization and more detailed sediment maps. Okay, this is what happens for the crustal thickness. Remember that if we only filled in the crustal thickness, or we actually had those profile measurements, we'd have a very splotchy map. Okay? Instead, we get something that I guess we think looks pretty reasonable, right? We've got really thick crust down here along the South American margin in the Andes. Up in Tibet, we've got thin crust in the Basin and Range and in the East African Rift. and of course quite thin crust in the oceans, except in areas where we've got some thickening by later volcanism. Okay, but it looks pretty reasonable, right? Okay. And you do the same thing for the velocity profiles as well. Let's see. Oh yeah, right. This is also how we can get an overall average histogram of what the crustal thickness looks like. So, I mean, basically, you can just look at the black line here. Here's the thickness and the percent of the surface area covered. These thin crust areas up to something like mostly here around 5, but up to maybe 12 kilometers. That's basically all falls out. That's the oceans. And then you have maybe some slightly thickened regions in the oceans, but essentially all this thick stuff over here is the continental crust. So kind of like the hypsometric curve, actually the crustal thicknesses fall out a lot like the continent ocean differences. Okay, and then I said you can do the same thing not just for the thickness, but for the velocity profiles. And so this is just the set of basic crustal types that were developed from the refraction measurements. So for example, here is what the P-wave velocity structure looks like if you divide everything into a few layers. You say everything in the world, I'm going to say there are 3 layers in the crust. You've got some sediments, and then you've got 3 layers of crystalline crust, and you've got a moho. This is obviously an oversimplification, right? Like, it's kind of like going out and saying, this mountain is made out of granite. I'm done. Okay. Because no, there's like a really special garnet over there. But okay. But basically, you have to do something. You have to make a reasonable choice. And so that's what they did. And so you can look at the thicknesses. This is where you go down into the mantle here and what the velocity of the mantle is right below that. You've got your lower crustal layers. That's all these guys with slightly varying P-wave velocities. Okay, mid-crustal layer, upper crust, and so on. And so you can see the variation. Here's a submarine plateau. Here's the ocean. You get the idea, right? Okay, so they have just these, however many that is, 14? Anyway, something like that. A dozen, basically, primary crustal types. And then they go and they actually adjust these around a little bit more because there's a bit more information about layer thicknesses in different places. So you end up with something close to 140 different crustal types that you use that discretized, pixelized geological map to distribute around the globe. Okay. Yes?
Did they change also the velocity or also the thicknesses of the...
Just the thicknesses in these extra 139. They are just changing the layer thicknesses and particularly the sediment thicknesses. That's the main thing that changes close to the surface. Yeah.
Do you know how they're going about refining crust to go to crust 1.0?
Yeah, so the question is, in particular, Gabi Lasky and Guy Masters have been working on refining this to a 1 degree by 1 degree model, which will be called very creatively crust 1.0. I mean, usually it's like it feels like we're going backwards, right? It's the opposite of computer programs. I think they should name it after an animal, but anyway, okay. Yeah, so the main advantage in going to the finer parameterization, it's not like there's suddenly a lot more refraction information about the actual velocity profiles. The big thing is to have a better representation of the known shallow sediment structure because the thicker sedimentary basins can make a huge difference in the overall seismic wave speed. I'll show you an example. So there's that, and it also allows you to do a better job of matching continent-ocean boundaries. So a big improvement between the 5 degree model and the 2 degree model was just by making that box smaller, you do a better job of representing the coastlines. And the same thing for going down to the 1 degree model. They're also incorporating there some constraints from surface wave observations. But the last thing I saw about that was that they hoped to have a new release of that August 2012. So, there's always something, right, that comes up. Okay, so that's basically how we do it, and then how do you get the other important pieces of this? That was the thickness and the P-wave velocity, right? but we actually want to know S-wave velocities and densities. Otherwise, there's a lot we can't do, especially since in the mantle, we're often also very interested in or can measure better the shear wave velocities. So the answer is you do it from scaling relationships, and there's a whole bunch of different sources for that, and I'll just show you 2 examples. So to get the S-wave velocities from the P-wave observations, they use results from Christensen, and these are measurements made on a whole bunch of different rock types. The ones they've labeled here are the ones that fall in weird places on the diagram. So the point is really that most of these actually scale very nicely for reasonable Poisson's ratios between 0.25 and 0.3. So Poisson's ratio being one of those elastic moduli that we talked about before. So you can do a pretty decent job here, but obviously you do have to be a little bit careful because not everything behaves in the same way. Okay, and then you do the same thing for density. Here are results from Christensen and Mooney developing a scaling relationship between density and the P-wave velocity. So in these crustal models, really, the density and the S-wave velocities come from scaling the observed P-wave velocities. Okay, and then we're also extrapolating from where we actually have observations, which is mostly North America, Western Europe, some longer range experiments in the former Soviet Union, and so on. But there's a lot of assumptions that are getting made here, right? So I guess a reasonable question is how well this actually works, because that's a lot of extrapolations. So I'll show you one way to evaluate that is to try and compare some kind of prediction that the crustal model makes with independent seismic data. Okay, and so I'll show you an example where it's now becoming possible to compare predictions from a crustal model like this with, say, surface wave phase velocities like Yaron was talking about before. Okay, so let me show that. All right. So if nothing else, we have learned that seismologists measure travel times. And so for surface waves, right, we know that different periods travel at different speeds. They're dispersive, but it's still true that our travel time curve can be constructed, and we can get the speeds from the slopes of those curves. And we also saw that waves with different periods have a different sensitivity to the structure with depth. So that is to say that if I change, let's say, my shear wave velocity at some depth, that's going to have an effect on how fast the surface wave propagates. But the effect that it has is going to depend on the period of that wave, right? So if I change the velocity structure at 10 kilometers depth, it's going to have a very big effect on a Rayleigh wave at 5 seconds period, okay? If I change the velocity structure, let's say down here at 20 kilometers depth, it's going to have a very big impact on surface waves at 10 seconds, and so on. Okay, so if we take our S-wave velocity structure from the crustal model, we can make a prediction of how fast the Rayleigh waves or the Love waves should propagate, and we can compare that to what we observe for how fast those surface waves propagate. Okay. Okay, so here's an example. These are, I'm not going to go into how these were made right now, but here are a couple of maps of observed variations in Rayleigh wave speed at 2 different periods. And these are represented as a difference in how fast the propagation is compared to the average velocity. So you say, in this case, I take all of North America, and I find the average, bless you, the average speed of Rayleigh wave propagation at a given period, and then I'm looking at a difference from that. Okay, so this is for Rayleigh waves at 5 seconds. This is from Rayleigh waves at 20 seconds. These are some, did I just say this? Like, my short-term memory is, okay. Well, if you ask me a question, you might have to ask twice. These are some maps that Yaron made recently. Here's 5 seconds up here. So these are very sensitive to the structure in the top 20 kilometers of the crust. Here's 20 seconds. Those are very sensitive to structure in this region down here. Okay? And so the red things are places where those Rayleigh waves propagate very slowly at 5 seconds, sometimes extremely slowly, 50% slower than the mean speed. And the blue areas are places where they propagate faster than the average. Okay, it's just a way of representing how those speeds vary.
Meredith?
Yes?
Why is the East Coast all white?
Oh, yeah, that's because these are made these are made from U.S. array observations, and the transportable array of the U.S. array just started getting installed in this region, so those data haven't accumulated yet. I'm sure if you ask him in about 6 months, there will be another few rows and so on. It's been kind of creeping across the map. So, right. That's the only reason. Okay. So you can see already that there's some correspondence with geologic structure, right? Big sediment piles down here. There's the Central Valley, a bunch of basins in the mid-continent. Okay, but the question is, that's the observation. If we make the prediction of what these should look like for, let's say, the Crust 2.0 model, does it actually match the observations? Because the idea here was we were going to test the crustal model. The answer is it does a pretty good job. So these are plots of correlation between the observed maps and the predicted maps at a bunch of different periods, which you just have to be like a geochronologist and read from right to left. Okay, these are the short periods over here and the long periods over here because it's in frequency. So these are 5-second observations like I just showed you in the map. Here's 10 seconds over here and so on. Love waves and Rayleigh waves. And the open symbols are the correlations of the observations against just the Crust 2.0 model over a 1D mantle. So there's no mantle structure in there. It's just the crustal model, basically. And so what we see is that over here at these short periods that, remember, are sensitive almost exclusively to the crust because of that sensitivity kernel, we see a pretty good agreement. Those correlation values are around 0.5. Okay, so they're not great, but they're pretty good. So overall, the model is doing a pretty good job. Okay, and then that's true for love waves and for Rayleigh waves, so that's a good sign. The place where they kind of fall apart over here and you get the correlations going towards 0 and even going negative at the longer periods is because the mantle starts to matter. So the filled-in dots are actually a comparison to a model that has Crust 2.0 on top of a mantle model that actually has structure in it, and so you can start to explain those. Okay, but so for comparing our model, we're really interested in these short periods over here. So it does a pretty good job. Yeah?
So where it doesn't correlate, is it just random where it's not correlating?
No.
Places where it's not necessarily correlating?
Right. Yep. So one of the biggest disagreements is actually in these places where you have like really deep sedimentary basins, for example. Really, so it actually does a better job on the fast velocity side than it does on the slow velocity side. Right? Yeah. Okay.
So you said it does a good job of correlating, but it was only a
0.5. I said it does a pretty good job. I mean,
So what? I don't know. I mean, so what we classify as doing a good job?
well, at least they're correlated. I mean, actually, I think when you consider everything that's gone into making the crustal model, that you have relatively sparse observations only of P wave velocity, and that these observations depend primarily on the shear wave velocity, where you got by a scaling relationship, and you're comparing observations that can now be made on, I think Euron's model is parameterized on quarter degree by quarter degree pixels, and you're comparing those observations to something that's parameterized on a 2 degree by 2 degree basis, that actually it's probably not that bad to correlate at the 0.5 level. Obviously, you'd like to have something much higher. If we compare just different Mantle tomographic models, they tend to correlate at the longest wavelengths, something above 0.95. So
You can think just square it, right? And think about order variations or explain.
yeah. So
Could some of this disagreement, if I may say, be due to the scaling relations that did you try to investigate?
yeah, so I think that's probably right, though. So that, I mean, basically, what this is designed to explain part of this. Where do the discrepancies come from? So here's an example. Here's love waves and Rayleigh waves for a location in northern Minnesota where the sediment cover is relatively thin, and so on. And actually, there's quite good agreement. The observations are the dots, and the predictions are the lines. So you actually get quite good agreement in a setting like that between the predictions and the observations. If you go down to southern Mississippi, where you have a huge sediment pile sitting there, you get decent agreement at the longest periods. This is like 40 seconds. But you go to the shorter periods, and it's just the velocities that you observe are down here around 1.4 kilometers per second, something like that, incredibly low phase velocities. So those are the kinds of places that are the worst predicted. And it may be that those are also the kinds of settings where not only the thickness is maybe not represented right, but where the scaling relationships are the least appropriate in those piles of sediments. So
this is the best case scenario because this is over the North America.
Exactly. That's right. Yeah, that's right. There's room for improvement. So I guess on the one hand, I would say it's remarkable how well the crustal model derived in this way does. And on the other hand, clearly, there's a lot that we're not capturing using this kind of approach. Right? It's certainly a lot better than saying, I made a measurement right here, and I'm going to apply that everywhere there's continental crust. But there's also a lot of... Yes?
Meredith, if you were to do the same exercise with the oceanic crust and lithosphere, would the correlation be comparable or much better?
I think it would. Okay, so I'm speculating a little bit, but I think it would be much better just because the oceanic crust is so much more uniform than the continental crust. But you also get very quickly into the mantle mattering because the crust is so thin too. But I think it would be better. Yeah.
I have a related question about the scaling. So just empirical fits to lab experiments, or
They are empirical fits to lab experiments, yes.
do you have a sense of where those scalings fall down? So, there's a complaint about the correlation at 0.5. At what point is it actually significant anyway?
At what point is it? What do you mean?
So, two questions. One is, do you have a sense of where the scaling is?
I think the scaling relationships are probably worst in the places where you have sediments that might have a lot of fluids in them, or I think probably in more standard crystalline rocks, you're doing a better job. And then I would guess that it's really places where you have scalings that that are a little weird, that aren't quite accounted for, because you've got to use a different scaling relationship when you have sediments versus crystalline rocks versus whatever. So they're drawing from a whole bunch of sources there that maybe could be revisited. Yeah.
And my second question is, how big is the correlation coefficient have to be for it to be significant? So 1 is perfect, depending on how you normalize the coefficient in the first place. Is 0.1 okay, or is 0.5 okay?
0.5 is okay. I'd like to see more like 0.8, 0.9. Yeah.
I may comment. I would guess the correlation is significant above 0.3 or something like that, because it has to do with parameterization of the model.
Yeah, we're well above a random. Yeah.
So 0.3 is like your noise floor.
Well,
Ish.
yes.
That sounds 0.2, 0.3. That sounds reasonable, but I don't know the answer.
But
So.
it really is not an important question, because statistically speaking, yes. I mean, crust
right. Okay. So yeah. Okay. So there are a few different reasons we even want the crustal model, right? One is that we actually want to be able to say something about the characteristics of the continents, which is useful to us in understanding how they formed and how we get rid of them. And then the other reasons are that if we want to be able to learn something about the mantle from a seismological perspective, we have to be able to get rid of the crust. So it's kind of a dual purpose thing there, and the same. So I think, yeah, you want to keep both of those in mind. I'm rambling now, but okay. Maybe that's enough about the crust. I think I was going to say,
I'm sorry.
yes.
This match is always on deep sedimentary basin?
No, not always. It's just preferentially there. So actually, I'm sure Yaron would be happy to tell you more about it. But basically, if you look at the range of observed velocities compared to the range of predicted velocities, you do much better on the high side than you do on the low side. The medians are not that bad, but there's a very wide range, especially on the low side, of observed velocities that just isn't predicted by the model. But it's not that it's perfect on either side. Okay, so I think we already identified some improvements are needed in the crustal model, and this was at the beginning of a long list, partly just spatial coverage, right, because we're really basing a lot on where those triangles were on that first map. So one thing that the surface wave maps that I just showed you actually have the promise to help do is to improve what the constraints on the crustal structure are, independent of just those refraction measurements. Again, right now it's going to look really great in North America, but you should be able to get some insight there and actually get a better mapping of the crustal structure, which you then ought to be able to use to infer something both about the crust in a geological sense and helps understanding the mantle too. That would also help us reduce the reliance on, say, the scaling parameters to obtain the shear wave velocities, because you've got something that's sensitive to the shear wave velocity. Of course, we talked about needing potentially better scaling parameters. The other thing that's not in any of these crustal models is anisotropy in the crust, and we do know that, meaning anisotropy, meaning that seismic waves can travel at different speeds in different directions, and that's not accounted for here. It's all those famous two elastic moduli for the isotropic medium, and it's just very poorly constrained in the crust at the moment. Roberta.
I have a general question about the crust 2.0 versus 2.1 models. You said that the main difference is going to be in the sediments, which they spent a lot of time working on. But my impression is, when crust 2.0 was compiled, that was actually quite a long time ago.
Right.
And there's been a huge amount of interrogation of the planet from seismology since then. Is it that people aren't doing refraction experiments so much, and why not?
Right. So the question is, I guess I said that there aren't that many more black triangles to put on the map, and I think that's basically true. It's not that nobody is doing refraction experiments in the continents, but it definitely is not the same kind of focus that it once was. Why? It costs a lot of money. You have to explode things, and I think the focus actually just shifted a little bit. So, it's possible that with some of the USA array results, there will be an increasing. Yeah, exactly. That the focus on the crust may come back a bit.
Eventually, someone's going to have to think about how to formally include things like zero function stuff.
Yeah, that's right. Okay, so.
Go on asking questions.
Yeah, that's right. So, okay, one thing, there's another type of constraint on the crustal thickness and to a certain extent on the velocity that I have a couple of slides way at the very end because it's about the mantle. But there are also ways to use passive source techniques. That is, you don't set off an explosion. You actually make measurements of converted phases from earthquakes that give you constraints on the crustal thickness and at least an average velocity.
Is Crust 2.1 incorporating those?
No, so none of the receiver functions are not included in the Crust 5 or Crust 2.0. I don't know what they're doing for the 1 degree model. I can check. It's complicated because you've got, it gives you mostly a thickness constraint. There's a trade-off with the velocity, and then you get an average velocity. Basically, it's harder to get out that layered structure. So what Torsten said is right, that some attention needs to be paid to how to include those constraints, since they don't just easily merge in with that particular approach here. But there's no reason it can't be done. It's just all of these things, right? I guess one thing to appreciate is how much work it is to go both from the seismological side and the geological side, and try and put all these pieces of information together.
It would be interesting to do an experiment for a place, where we have lots of receiver functions, like North America now, US array, to do something like a merger of a sedimentary thickness map, where we receiver functions, but then do something smart to get rid of the trade-off, and then see if that outperforms everything else out.
Yeah. Now, I think there should be a lot of opportunity to improve this, especially for North America in the coming few years.
I think there's quite a few groups working on combining receiver functions with surface waves.
That's right.
With,
Yeah.
detailed structure.
No, of
That's right.
course. I mean,
It's just maybe not in this particular project of Crust 1.0.
Right. Well, I guess the broader statement would be that people are working a lot on incorporating receiver functions and phase velocity type estimates together in one model. And then we have this whole data set of things that are primarily sensitive to the P-wave structure, and putting those two types of things together is a kind of a clear next step, and is not trivial, but it should be done, right? Okay, so I kind of want to talk about the mantle. But do you guys have something about the crust that you think about it? Yeah.
What is the primary control on, say, the 3 crustal layers?
Oh, like why did they choose 3 crustal layers?
Those 3 velocities.
Right.
I guess what evidence is that based on?
Right. So they chose 3 crystalline layers in the crust, basically as a reasonable compromise between the actual observed individual velocity profiles and something simple. So it's pretty clear that you can't do a very good job explaining the crustal structure if you just make it one layer of a constant velocity. And the problem becomes a little bit intractable if you have, let's say, 12 layers in some places and 2 layers in another place. So it's sort of a balanced compromise. It's not because there's any evidence that everywhere in the crust there are actually 3 layers with discontinuities between them. So it really is a choice that you have to balance reality with what you can actually represent in the model. And then the velocities within those come from taking lots of velocity profiles in a given crustal type and saying, okay, so in that top, the thing that we're going to define as our top layer, this is essentially what the average velocity looks like. And those have already been kind of grouped, kind of an informal version of a cluster analysis. I guess these all look like each other. And so taking a representative velocity in each of those layers. Does that kind of, yeah?
I guess, is there any sense for how accurate that methodology is, or if that's a major source of uncertainty?
Yeah. The extent to which that approaches an uncertainty, I guess, partly you see it in the comparison. One way to answer that is to look at the comparison like the one that we just looked at. And, probably in some cases you could do a little bit better by adjusting those layers up or down or introducing more layers. But, overall, it's probably a very reasonable way to approach the problem. Unless you have more specific local information. I'm sure you can always do a better job in any given location by doing something else. But on the broad scale, it works pretty well. Any other? Okay, let's talk about the mantle. Okay, so here was that correlation picture again. And basically out here, this is 40 seconds out here, at these, what I still think are relatively short, but are longer periods for both the love waves and the Rayleigh waves, when we only have the crust, we actually get essentially nothing out of the crust. It's not helpful to us. We can't explain the data with just the crust. We actually need to include the mantle. So these are predictions that include both the crust and a 3D mantle model, and they do a lot better. You can also see the need for including the mantle in the continents if we just go and look at dispersion curves for particular locations. So these are the curves of velocity as a function of period, now at longer periods and going in the direction where you read to the right to get to longer period. For two different locations. This is somewhere in Indiana and this is somewhere in Oregon, so not tectonically active and tectonically active. The dashed lines are the Rayleigh waves and the solid lines are the love waves. And these are actually plotted as the difference from an average. So there's already an average taken out of there. But the main point is just that they're different. Over in Indiana, you see that everything travels basically faster than the average until you get to the shortest periods. And in Oregon, tectonically active, much slower. Things are traveling slower than the average. So there clearly is a difference in how fast the waves propagate in different regions of the continents. That's due partly to the mantle. You can see that here too. This is like that comparison we made before. Here's a prediction of now for love waves at 40 seconds, how fast those waves should propagate if we just have the crust. And then here's the map version of what we actually observe. So you can see over here, the slow part does kind of okay. By the time we get over here into eastern North America, the crust is still thick, right? So we still have slow velocities compared to our average. The oceans are the fast stuff. But we're actually seeing faster velocities up here where we've still got thick crust. And that's really the effect of the mantle coming through. It's telling us that the crustal model is not explaining the whole data set. So I want to say something, like basically 2 slides, about how we even know what this structure is and how we can get the 3D structure out of these kind of observations. Because I showed you the maps. These are all based on a form of travel time observation that we said we can get the velocities out of, right, between our source and our receiver. But then how do we actually turn that into a map that shows us these lateral variations in velocity? Because it's very apparent that if we're going to talk about the continents, we have to have some kind of lateral variation. Those 1D models like PREM are not going to do it. The continents and the oceans are so different from each other that we have to be able to explain lateral variations. So this is actually what the tutorial tomorrow is kind of about. So this can be very brief and just conceptual about how we turn individual measurements of travel time or speed on a single path from a source to a receiver into a map of velocity variations. So here's the Earth, and we just want to represent what the velocity variations on some part of the Earth actually are. So I've divided the Earth up here into little squares, 70, 80, 90, 100. Okay, they're 10 degrees in this case. Doesn't really matter. You can parameterize a model any reasonable way that you want to. You've got to choose some kind of function on the surface of the Earth. And you're going to say what the velocity is there. So for example, here it's in blocks. And what I want to figure out is the most representative wave speed within that block. And I want to do that for all the blocks. Okay, I could do it in spherical harmonics. I could do it in splines. I could do it in whatever. But if you do something sensible, it doesn't matter which of those you do. So blocks are easy to visualize, so we just want to figure out what is the wave speed in each of those blocks. And so we have, let's say, an earthquake down here, and we record it on a station over here, for example. And so there's the path that the wave traveled. So if I have a measurement of the travel time, that gives me the average wave speed on that path, then I can say that I know the average wave speed on that path. Well, that's very nice, but it crossed a lot of little squares to get up there. So what I know is this average. Maybe it was it arrived kind of faster than the global average, but I have no idea where on that path the fastness came from, or whether it's actually just a single velocity along the whole path that it's seeing. Okay. So how do I fix that problem? More observations. That's a great idea. On the same path? Different path. Okay. More observations on a different path. All right. So then we take an earthquake here, and we record it up there. And so then let's say that one's actually slow. Then I can say, well, probably the fast thing on this path didn't come from in here because that one was slow. So we've got some improved constraint right here. It's going to take us a long time to fill in the Earth here, but okay, there's another one. Now we're going to be able to say, all right, we've got two places where these cross. We can sort this out. And we keep adding these things on, right? Because we want to cross all our paths, and in fact, we want to have more than one thing crossing each path. So we can back out where was the thing that made one of them fast and where was the thing that made the other one slow. You guys are looking at me like, yeah, okay. So, I mean, it is basically that simple. You just, in principle, implementation is always a different story, right? But okay, and you want to eventually, see, you're supposed to be, like, we add on the little paths here, and you want to cover all the boxes. You get the idea, right? Okay, you want it to look like that, all right? Okay, that's the goal. Okay, so once you've achieved that, then you do actually get, okay, so those were ray paths from a real model, and if you keep adding on all the ray paths for that particular model at the size that I drew them in the example, you will actually end up with something like this, which doesn't mean you actually have perfect coverage, but actually we do pretty well. So the data aren't perfect. We get good coverage. We still have to make choices. It's not like this just automatically is going to tell you what the velocity structure is. We're going to talk about some of those tomorrow. But actually, in general, we can do a pretty good job of backing out the wave speed structure when we have a lot of paths like those that cross each other and cover all of those boxes. Okay, so that's the basic idea. Does that make sense? Yes. Okay. Okay, so then if we do that, then we can develop maps like the ones that I was showing before. This is a global example, love waves at 75 seconds. And they're shown as the deviation from the global mean speed. So Yaron was making the point that actually everything is pretty well explained by a 1D structure. So that's true, right? Because these are very well-resolved deviations from that mean speed, and they range from something like minus 9 or 10% to plus 4% in this case. And at shorter periods, the range is a bit bigger. We saw that for the very short periods in the crust, obviously, you got much bigger variations, 50, 60%. But in general, what we're looking at are relatively small variations, but important. And you can see features you might expect, very slow wave speeds along the mid-ocean ridges, and then faster wave speeds in the old Cratonic regions. Okay, but these are, again, for the surface wave phase speeds. They're like the gray boxes that Yaron showed. You're just measuring how fast the love waves travel across the surface of the Earth, which is good. But remember that we also know that at different periods, the waves travel at different speeds. And in addition to that, we know that waves at different periods are sensitive to velocity structure at different depths in the Earth. Okay? So this is one we saw before. Here are longer periods. If you go all the way out to, say, 350 seconds, we actually have sensitivity all the way down into the transition zone. So we can use the combination of the fact that we have, that we can make a map of how fast the surface waves travel across the Earth, combine that with the fact that they have different sensitivities at different depths, and that allows us to back out then what the underlying shear wave velocity structure is as a function of depth, not just laterally. Is that? There almost always is a question about this. No, there's not. Okay. So surface waves I'm emphasizing a little bit because they're a very important constraint on the shallow mantle structure because they have such good sensitivity up here in the shallow mantle right under the continents, which is where we're gonna look. But obviously, there are a lot of other types of data constraints too, everything from the normal modes to the high-frequency travel times that you saw the travel time curves before. And it's really the scatter in these travel times from a perfectly thin line that is responding to the variations in the velocity structure laterally. Okay? So if everything were exactly a 1D Earth and you could pick your P waves perfectly, these would just be very thin lines. And instead we've got this scatter around there because some of them arrive a little early, some of them arrive a little late. So use those in the same way as the red lines on the map. Put all of those together, okay, then we get images of variations in wave speeds throughout the mantle. I think that's good, right? That's exciting. So really, okay. And this is just an example of one model from Bogdan Kustowski. 100 kilometers, these are just slices through the mantle, 300, 600, 1,000, 2,800 kilometers right at the bottom of the mantle. Plotted again as deviations from an average at each depth. You can see up here something like plus minus 5%. The amplitudes decrease as you go deeper in the mantle. Now we're down to something like 2% down there. And you can see very good correspondence with tectonic features at the shallow depths. You go down to 1,000 kilometers, maybe not so much. Okay? So what we're going to focus on for like my few remaining minutes of the continental mantle is mostly this shallow part because it's sitting right underneath the continents, right? But I think it is actually worth remembering that we shouldn't just ignore whatever it is that's going on down here in the lower mantle because there may actually be some important ways in which the structure at the bottom of the mantle controls tectonic behavior at the surface. So the whole mantle is connected to itself, so let's keep that in mind, but I am going to focus in on the shallow part. Okay, so here are a whole bunch of tomographic models made using a different combination of all those different types of data that are measured in different ways and whatever, plotted at 70 kilometers depth. And, okay, this study, that doesn't mean I did it. That means Bogdan did it, and I took his slide. But a very good correspondence with tectonic features, shallow. The mid-ocean ridges are hot. You see the seafloor cooling signature, and you see these very fast velocities, something like 6-7% fast, very closely aligned with cratonic regions in the continents. It would be easier to see if Africa hadn't been split in half, but there you go. And that's true in all these models. They differ a little bit in the details, but those same features really show up across everything. This one is actually not based on an inversion. This one is actually based on saying, okay, we think we know what the geology is, and let's predict what the velocity should be. So it's kind of a way to see that, yes, in fact, where there are cratons, you observe fast velocities and so on. Okay? But they all really look, these are not features that are very model dependent. They really just show up and won't go away in every model. Okay, so 70 kilometers. Yeah.
Under Tibet, where it's fighting its low velocity, is that
Yeah.
just the crust is thick, or actually?
So the crust should have been taken out of all of these models. The crust should have been accounted for. So it's always, if the crustal model is not quite right, you do have to be careful about the signal bleeding in there. And I can tell you, like,
I guess I'm asking because you're at 70 kilometers.
Yeah, right. I see what you're saying. Okay, we're at 70 kilometers. So, for example, in this model, which I know the answer because I made it, that is actually a very I put the crustal model into the whole model. So there, in some couple of places, you would still be in the crust, and that's why it's slow. In the other ones, it's not quite handled the same way. Maybe don't interpret Tibet in this model, in this depth. That is probably the good answer there.
They use always the same crust for the different models?
No, the crust is handled in different ways in the different models, depending on the modeling approach that was used. So, and this is a depth at which you are going to see some effects of errors in the crust. So actually, it's kind of a good sign that the models all look so similar, because the crust is handled in a different way in the different models, and yet, you are getting out the same mantle structure. Okay, so then if we go a little deeper, here's 150 kilometers, 3 different models. And again, the models look quite similar in their key features. And we still see the tectonics. We still see really strong signatures from the cratons. We see some parts of the continents, of course, are not cratonic. So we see slow velocities under the basin and range, for example. Okay, and then we go down to 250 kilometers depth. Again, same basic idea. The signal is weaker. The perturbations aren't as strong. But actually, we still see a difference between the continents and the oceans. Okay, and this is a quite robust feature, that even at 250 kilometers depth, there is a difference seismically between the continent structure and the ocean structure. Okay, that does go away eventually. Here's 600 kilometers depth in a whole bunch of models again. And Barbara pointed this out yesterday. Now what you really see is blue stuff around the Pacific and so on. But that's not, that's like subducted slabs and et cetera. So you're not seeing, for example, the fast velocities associated with the cratons anymore. You're not really seeing the mid-ocean ridge signals and so on. So somewhere in there between 600 kilometers and 250 kilometers, that signal went away completely. And where exactly that happens is, I'm not going to tell you that answer. It's going to depend on how you, that is going to depend a little on the model and how you interpret it. But it's quite robust that to at least 250, maybe 300 kilometers, you do see a difference between the continents and the oceans.
I would say the other way around.
Okay.
If there is a difference down to maybe 250 or 300, we can argue about it, but it really disappears there.
I think that's, what did I say? I agree with what Barbara said.
Like somewhere between 250 and 600.
Oh, okay, right. I meant that I have, it's very clear that it's gone at 600. I don't think it's at 400. Probably it's not at 350. It probably is around 250 to 300. But like Barbara said, you can argue about or we can say, we can discuss it.
By now, we know pretty well that below 300 kilometers, the differences are much, much smaller, the natural variations.
They are much smaller, yeah.
I mean, I don't want anybody to get the impression that down to 500.
This, of course, depends on the resolution of the surface wave that at this depth we only don't figure the centering the Earth, so somehow.
So the question is about the depth resolution in the models. Yeah, but these models are not dependent only on surface waves. There are a whole bunch of data sets. So I actually think, I agree with Barbara. I think it's not a question of model resolution whether the differences persist to 500 kilometers. I think it's pretty clear that they don't. And where we're arguing about is sort of in that 50 to 100 kilometer range between 250, 350, something like that.
And talking to students, there is a poster on this subject arguing for Craton structure going deeper than that.
Okay, well, then you better go to the poster session too and form your own opinion.
I could argue quite against it and say that it's an effect of anisotropy. 2 points of view.
Okay, so clearly, right, so this is actually, this is why I think the continents are about the mantle, right? Because there is something interesting and weird going on here, that the signal actually does go down so deep, and understanding how deep it actually goes should tell us something about the continents, right? Okay. Yeah, so that was that. Okay, so if you just needed to be even more persuaded that there is something different between the continents and the oceans, you could do something like what Barbara showed yesterday with the cluster analysis and let everything regionalize itself. Another approach is to take a description of the geology and say, I'm going to take average velocity structures under, let's say, all the cratonic regions. I'm going to take everywhere there's a craton and average out what those velocity structures look like and compare them with everything that's under a tectonically active region. And it turns out that whichever way you go with that, you get a similar result. Do you see that this is the Earth? This is like the Earth in ASCII art. This is like, yeah, anyway, it's kind of, some of us still do beach balls in ASCII art too. But okay, so this is a regionalization of the Earth that Tom Jordan made about however many years that is, 1981. P, Q, S, A, B, C. A, B, C are different ages of the ocean, and then the P's and Q's and S's are different types of continent. Okay? So here's what you get if you, I did this for a model I made because that was easier, but it looks quite similar for other models. If we take all the oceanic regions and take average shear wave velocity profiles, so here are young oceans, depth versus velocity. Here are middle-aged oceans. These are student stipend oceans. These are postdoctoral oceans. Okay, anyway, and these are distinguished oceans. And you can see that as the oceanic lithosphere cools, the velocities increase. The depth of the low velocity zone gets a little bit deeper, but basically behavior we can understand based on thermal cooling. In the continents, you also see differences. So here are orogenic and magmatic regions, slower velocities, still faster than the young oceans. And then these green and blue ones are quite fast in the shallow part of the mantle. And the low velocity zones are quite deep. There is a low velocity zone there. So basically what we saw in the maps, but just that it does actually agree with the surface geology on this level, similar to what Barbara showed you. And we can talk about the details. Yeah?
Following what Barbara said here, on the oceans, you see the variations between young and old oceans very big compared
That's
to
right.
what we expect.
Yeah, that's right. Yeah, no, that's right. We do. So it is. There's a lot to talk about in the oceans too, but it is also quite clear that there are variations in the oceans to well below 100 kilometers, certainly 150 kilometers, and potentially a bit deeper than that, and then also in the continents. Yeah.
On your previous map, you suggested the differences between 250 and 300, but on that cross section, it looks like the low velocity zone under the cratons is about 150 kilometers.
The low velocity zone under the continents is somewhere here around 175, but so this is a point that hopefully we can come back to later. These velocities are still much faster than the global average, all the way down here at 250 and close to 300 kilometers. So, if you look in the maps, you're going to see a blue spot there. You look in the profiles; these are still. I should have put the global average on here, but this is still fast, and this is still slow compared to the global average at that depth, even though you are within or below the low velocity zone. So that's actually an interesting question. What's going on there? Okay, I wanted to show. Yes.
Based on that figure, how thick a lithosphere are you putting up with a Precambrian? Basically, a straight line.
The question is, how thick is the lithosphere in the Precambrian?
Yeah.
Well, I think what is the lithosphere is a big discussion, and it's pretty hard to pick a lithospheric thickness off here, and it depends on what you mean by the lithosphere. A lot of people on surface wave profiles will pick either the minimum velocity down here or the steepest gradient as the lithospheric thickness. So if you did that on this, remember this is an average profile, it's not for one place. If you did that on here, it would end up somewhere around 100 kilometers, and yet it's very, very clear that there are fast velocities associated with that continental material much, much deeper than that.
I would point out that other models have different profiles.
Sure.
Much faster velocities down to 200. I mean, the steepest negative gradient is much deeper.
Is deeper, yeah. So that's right.
I was wondering approximately where the average adiabat intersects the solidus under the continents. Where would that fall?
I have a picture from Cinti later. Let's come back to that. That's a great question. Okay, I wanted to show another characteristic of the continents that is potentially important and interesting. It requires introducing another seismological concept, which is of anisotropy, which we said means that waves propagating in one direction travel a different speed than waves propagating in a different direction through the same place. In the Earth, an important type of anisotropy in the upper mantle is what we call radial anisotropy, which is a polarization anisotropy. And I showed you in the maps, wherever they went, something that's called shear wave speed or perturbations to shear wave speed, VS. And that's actually kind of hiding something in there because there's really more than one S wave speed. That is to say that in the upper mantle, shear waves that propagate with one polarization propagate at a different speed than shear waves with another polarization. So this is what PREM looks like. We already discussed the 220, but you can get rid of that. You still need the anisotropy. And shear waves with a horizontal polarization propagate faster typically than shear waves with a vertical polarization. Not always, but typically. So what does that mean? If you have an S wave coming in here to your receiver, Yaron talked about how S waves are transverse oscillations. They oscillate this way while they're moving this way, right? But that means that oscillation, if the ray is going this way, that oscillation can be in and out of the board, and it can be in the plane of the board with the wave propagating this way. Is that? Yeah, because, right? I'm going this way, and both directions are transverse. Yeah, okay. I didn't bring this Slinky. And those waves with those different polarizations can travel at different speeds. And so in the upper mantle, they actually do. And, with a characteristic that looks something like this. Turns out that love waves are mostly sensitive to this red one over here, and Rayleigh waves are mostly sensitive to this VSV. And so we're able to map out that anisotropy. It's not as easy as isotropic wave speeds, but you can do it. Okay, and it can arise from the anisotropy of individual crystals, that waves propagating one way through a crystal will propagate at a different speed than the other way, and you can align a lot of those crystals like little bugs down here. You can also get this type of anisotropy from layering of materials with different wave speeds. And so either of those could explain what we see in the upper mantle. I don't think we know what the answer is. Okay, so my point is just that we can also estimate how big that anisotropic signal is, where what I mean by that is how big the difference here is between SH and SV by using the love waves and the Rayleigh waves. And if we do that, and this is, I think that the maps I showed you of the isotropic velocity structure all agreed with each other quite well, especially at the longest periods. That's, I would say, not as true. That's not quite true for the anisotropic structure. There's pretty good agreement on the longest wavelength structure, but it's much more difficult to constrain than the isotropic structure. So here's one example. The isotropic variations, equivalent isotropic variations, and anisotropic variations at 3 depths. And the structure is, I think, different between the continents and the oceans. At the shallow depths, we have quite strong anisotropy under continental regions. Somewhere around 150 kilometers or so, we have the strongest anisotropy in the oceans, and then the strength of that decreases quite a bit at greater depths. And this is not something where every model looks the same. The largest scale characteristics are usually similar. And if we go and do an exercise like we did before with the regionalization for the isotropic velocity, do that for the anisotropy, then typically, and some people are definitely going to argue with me about this, but what we find is that the strongest anisotropy in the oceans is maybe just below the low velocity zone in the low velocity zone, somewhere between 100 and 150 kilometers depth. Whereas in the continents, the character is quite different, and the largest anisotropy is found in the shallowest regions of the mantle, decreasing with depth. And there's potentially a secondary maximum in that Barbara has actually mapped out and pointed out under the continents. But it looks quite different between the continents and the oceans is the main thing there. And we can talk more about that. I don't know why it is, and so on and so forth. Okay, it's almost 12:15. Yeah.
Numbers in perspective.
Yeah.
What kind of anisotropies do you expect with this concept? Is it comparable to the anisotropy in the mantle? Much smaller?
In the crust?
In the crust.
You know, I don't know, because crustal rocks can be very anisotropic, but then it all depends on how they're arranged in a bulk scale. So there are some observations of something like 10% anisotropy in the crust on the bulk scale, but those are made in very local areas.
Yeah, that's a particular region.
Yeah.
Related to some foliated terrain.
Right.
Like that.
So I don't think we have a great handle on what the anisotropy in the crust is in any general sense.
Basically, it's more in the shallow part of crust. In the middle and lower crust, actually, it's less. And that's basically true for until the eastern part of it.
Right. So I don't think we have a good sense in general. There are observations from a few specific places, but.
Because if you consider the lithosphere,
Yep.
then the anisotropy strength there is broadly consistent with some frozen in remnant of the kind of process that seems to be causing the anisotropy.
Right.
There's a broad, the numbers sort of match.
Right. So you can get a pretty decent explanation for that. Okay, Torsten's saying that it has to be frozen in because it's quite shallow and the wave speeds are fast there, and you don't expect that something happening at or above 100 kilometers is going to be caused by modern day flow in the mantle, whereas something like the anisotropy down here in the low velocity zone might be. So you could explain that by frozen in signal from previous mantle flow. You could potentially also explain it by building that part of the mantle through a process of layered structures. If you were somehow stacking pieces in there to make layers of alternating velocities, you could get something similar. I think, yes.
Please go back to one slide. Yes. Here, for the anisotropy variations, I have a question. So it shows plus minus 5, and that picture I think is taken and it's obtained from subtraction of two different models from SH and SV.
In this case, it's a difference between SH and SV models. That's not always how it's done. Yeah.
What other biases do you think might also involved in this picture? Because SH and SV, we know that they are not always providing the same data quality or same amount of data, so this could be also biased by some other.
Right. So the reason, so the main reason that anisotropy like this is more difficult to constrain than the isotropic structure is that you really need good observations of the love waves. And the love waves, because they're transverse motion, are recorded on the horizontal components of the seismometer, which are always noisier than the vertical component, except in some bizarre cases, but almost always. So they're a harder measurement to make. And when you can make them, then remember that the pictures of the sensitivity kernels, they're not the same shape for the love waves and the Rayleigh waves. So it's not like the love waves at a certain period are telling you about structure at the same depth as the Rayleigh waves of the same period. So that difference in sensitivity means that you have to have, in both cases, good data across a very wide range of frequencies so that you constrain the structure at all depths. So it's simply a harder measurement and to make and to interpret. So that's why it is much harder to constrain the anisotropy than the isotropic structure. So all of those things contribute to that.
There's also a second-order effect.
Yeah, that's right.
Sensitivity to anisotropy is much smaller to the sensitivity than the sensitivity to isotropic.
Right. You can't explain the bulk global data set without anisotropy in the upper mantle, but that effect is a few percent compared to the other variations that we see that can be much bigger. So that's another thing that makes it difficult to pull out of the data, because the first order thing is the variation in the isotropic velocity.
For what it's worth, we're going to talk a lot more about it.
Yes, right. I should have said that. Yes. Maureen is going to talk all about anisotropy. So I really wanted to point it out as something that is happening in the continents, and if we could understand it, would be very... Okay, right. And then that'll give us a couple of... where's the time master? We're doing a lot of discussion as we go along here. Can we... Okay.
You have another 10 minutes.
Okay. All right. Okay. So the thing that I want to try and get to here is, all right, so we said that the variations in the cratons in the mantle, cratonic mantle under continents, extend quite deep. So more than 250, definitely less than 500, probably more like 300, 350. This is not a new observation. And there's a very well-cited paper pointing out that there must be very deep variations between the continents and the oceans that Tom Jordan wrote in 1975 in a series of papers following on that. Now here, okay, so this just says that there has to be a variation under continental regions. He argued that it should exceed 400 kilometers. I think we raised that a little bit. It probably doesn't have to go to, I don't know, does Tom still say 400?
Look at the poster.
Okay. Okay.
Not quite 400, but close.
Okay, so he still wants them pretty deep. We've got some discussions to have here, but the main thing is this is obviously not a new observation, but we have much better control now on the spatial variation, what this actually looks like in a 3D sense, than we did in 1975, which is good, because if we didn't, then, yeah, anyway, okay. So in cross-section, these look something like this. This is taken across Canada. So here's where we can argue about how deep they are, even within a given model, right? Because this stuff is all fast. The zero contour is, I think it's this one right here. So if you go anywhere that's faster, then maybe here you would say, okay, 300 kilometers. But arbitrarily, a lot of people take 1%. So then that would be more like 250. Okay, and then you start to argue about how well that particular thing is resolved and so on. But really, those are arbitrary numbers. It's clear that they're deep, and you've got to decide what you mean by the depth of this thing. And weirdly, remember also that, at least I think, you are in the low velocity zone here. These are perturbations compared to an average at that depth. So you're faster than the global average, but it doesn't mean that in an absolute sense you're not seeing a low velocity zone. And here's a picture of the anisotropy. Don't interpret the details too much, but it's bigger at shallower levels. Here's that kind of secondary increase down there that also was discussed in Barbara's paper with Yuancheng Geng. 2003, I think. Another example of the sort of come farther south. Okay, again, here's that deep, fast velocity stuff. Of course, this is continent 2, and we've got really slow stuff there under the basin range. Here's that high anisotropy, and again, potentially a secondary increase compared with the anisotropy structure that we see out here in the ocean. It's quite different. Okay. What was I going to do here? Okay, so these things stick way down into the mantle, and we're debating the depth. Right, 70, 100, 150, 250. And I guess the question is then, like, how do we explain these roots? What are they doing there? What are they made out of? What's going on? And, up front we can say we actually don't have a great explanation for that, but there are hypotheses out there. And normally we associate fast velocities with things that are cold. Works well in the oceans. It turns out that if you try to explain these seismic velocities, these fast velocities, just with colder than average material, it doesn't work. It's not consistent with other observations, including the gravity field. So, for example, if we have something that is very cold, what should happen to its density? Increase by a lot, right? Okay, and so if it increases, if the density increases, that's a mass excess, and what happens to the gravity field? More mass. Right, okay. And so if we look in these regions where we have those big continental cratons, in fact, what we see is very small gravity anomalies, not more than 50 milligauss, and they're in the wrong direction. So clearly, whatever is down there is not just giving us a gigantic mass excess. And we can quantify that, which I'm going to skip through part of this because we don't have time. But if we can turn our seismic model into a density model, then we can predict the gravity field and see how badly we're doing. We have the crustal density structure from Crust 2.0, for example. And then we want to get some scaling for the mantle. So we know S-wave speeds in the oceans agree pretty well with the temperature signal. Here's the mid-ocean ridge, and it's cooling down that way, and the velocities get faster. In fact, if we just go and sample velocities in the oceans, figure out the age, and say I'm going to do a half-space cooling calculation to predict the density, then here's the correlation that we get between perturbation in velocity and perturbation in that predicted density. They agree pretty well. We get some scaling relationship between there. Happens to turn out very close to estimates from laboratory experiments. So let's just use that. We can go and predict the gravity field from the crustal contribution. That's just the densities from Crust 2.0. We can do the mantle contribution now just using only that thermal scaling, even though I told you that it won't work in the continents. If I just say all the perturbations in the mantle are thermal, then this is the contribution. And if we add those up, there's what we get for our total predicted gravity field. And let's compare that with the observed. And, okay, no real surprise, we've got this huge predicted positive gravity anomaly under the cratons, where we simply just don't observe that. Okay, and that's from the fact that we said all of the fast velocities in the craton were controlled by thermal variations. Okay, so that makes them very, very cold and very, very dense, a lot of extra mass. And this just emphasizes the same thing. This is just plotting everything bigger than 50 milligauss. So you really see those cratons pop up like that. Okay, and so Tom Jordan suggested, and a lot of other people have worked on since, including Sin-T, that maybe those temperature gradients, maybe it's cold in the cratonic roots, but maybe that is actually balanced out by a reduced density due to a compositional variation. So we're making it denser because we're making it colder, but maybe we can balance that excess density by reduced density from composition. That is, let's say that we extracted an iron-rich melt from those cratonic roots. We take out iron. What does that do to the density? Density decreases, right? So if the temperature decreases, density goes up. If we take out iron, it goes down. Turns out both of those things make the shear wave velocity go up. Okay, so we could get a very fast shear wave velocity while balancing our density so that we don't get this huge anomaly. Now, this is a very special thing, right? Because it means that you have to get no gravity signal, you have to very carefully balance exactly your temperature perturbation with your compositional perturbation. And the strict interpretation of this so-called Isopicnic hypothesis is that at each depth, those effects cancel each other out. So let's just say that's what works. We've got a thermal scaling from the oceans. If I can go and take a compositional scaling from Sinti's work, then we've got density as a function of mg number and Vs as a function of mg number. So we can put all those things together. We don't have to go through this whole thing, but if I do that, take thermal scaling from the oceans, compositional derivatives from Sinti's work, some people like other derivatives, then actually we can work out that for a depth of 100 kilometers in the cratons, this is with the requirement that the densities balance from composition and thermal scaling, then about 85% of our signal comes from temperature and 15% from composition. And we can work out what the perturbations to temperature and composition would be, cold by about 350 Kelvin and increased mg number compared to some reasonable background by about positive 2.5. And those are kind of actually in the ballpark from observations from other data sources. Okay, but that's also like one test depth with a lot of assumptions on it. And I think what Roberta said the other day was that the amount of depletion doesn't vary much with depth, which sort of makes it impossible to do this in at least a literal sense. So that would be an interesting thing to follow up on. And of course, there is debate about the compositional derivatives and so on. So we have a lot of questions still left open about the mantle under the cratons, some of which are here. And I'm sorry, I didn't get to the part about the lithosphere-asthenosphere boundary here, and we're not going to fit that in, but Kate Riker, I think, will be here at some point in the future, and we can talk about that maybe separately. So I know people are interested in that, so I tried to put it in, but made it by mistake of putting it at the end. So basically, I think the point is that there's a lot that's interesting in the cratonic mantle, but even now, after many years of working on this, there's a lot that we don't know about that. There's still 2 minutes before 12:30.
All right, I think we should spend 5 minutes taking additional questions or additional discussion if there is some.
Yeah.
Naive and maybe not a simple answer. When you look at the different velocity models, can you attribute the variation in the models to a few simple choices? And can you kind of comment on that? Or is it so complex to kind of deduce what's causing the variation?
Okay. Yes and no. I mean, first of all, overall, those models look extremely similar to each other, especially at the longer wavelengths. And the differences are mostly in the things that are harder to constrain, things like the smaller scale structure, the anisotropy, and so on. There is usually not one simple choice that's going to explain the difference between two models. The tutorial we'll do tomorrow will let people experiment with things like, I said the data are not perfect, so we do have to make choices, and those are in things like how you parameterize or describe the model, how you regularize the model to account for imperfections in the data. In cases like this, I guess the nice thing is that those kind of choices, which are different for all those models, are clearly not the thing that's driving the differences in the model because they end up looking quite similar. But those choices become more and more important the less well-constrained the problem is by the data. So they're more important for things like the anisotropy, the smaller scale structure, and to a certain extent for things like the details of how deep are those roots and so on.
Yeah, maybe I want to follow the discussions. There are some points I think that are crucial. Maybe we have to work a little bit about this. I mean, there are some we've seen that there is a very consistency between all the models because of long periods that they are sampling very well the Earth. But still, we see that there are some discrepancy. For example, all the models that they have this 1% of anomaly at 300 kilometer depth is, you said that is arbitrary. So I think that it's very important for the community to know how well constrained it is to have these isotropic variations of 1%. I mean, if it's possible, for example, to have a model that doesn't have this 1% but 0.1% and will fit the data equally well or at least satisfactorily. I think this is a very important question. And again, I want to push that also all the seismic models that show below oceans that the lateral variation in the isotropic part, that is the most constrained part, is much deeper, or what we think that is well known, the thickness of the plates that
right. So I think a couple of things there.
Kilometers.
Let me clarify what I meant by that 1% was arbitrary. What I actually meant was that when people try to say how thick are the roots under the continents, a common choice that is made is to say, I'm going to choose the depth at which they're 1% fast. That number of 1% is arbitrary. You could choose 2%. You could choose.
Yeah, but
and then the second part, yes, that is the details there. I think there's an underlying question of where does it make sense to say, what is actually physically important there? Is it important where the depth of that 1% is? Maybe there what we're looking at is only a thermal effect in the mantle from something cold above it, whereas we're looking at some other structure. I'm not saying this is what I think is happening, but we need to also figure out what is the important thing to be looking at. I understand your point about resolving whether 0.1 or 1% can be resolved, right? But what was the second thing you said?
No, I think that the same, but also below the oceans. I mean, we
need to, below the oceans,
as seismologists, we really need to put uncertainties on what we can resolve and what is not, and provide models that, if you want to address the physical meaning, is very important.
The uncertainties, I gotcha. I do want to say about this thing that the variations in the oceans go well below what the plate thickness is supposed to be. That is a well-constrained observation. So, the fact that there's a difference between the continents and the oceans down to 250, 300 kilometers is not coming just from the continents, right? That's also coming from the oceans. So that's also an interesting question. But
hello, I have two questions. And the first one, maybe it's not like questions, like kind of comments. Can you please go back to one slide?
Not that
maybe
one.
even further. Yes, so if I'm not wrong, this indicates a strict isopicnic status. Right. Not possible, right? It's not possible. It's not quite possible.
No, what this would indicate is that if this is the only calculation you could do, you could actually explain things with an isopicnic hypothesis. The thing that, but I did this calculation just as an example to say, okay, look, if I take this approach and I select, let me arbitrarily do this at 100 kilometers, you actually get something that's in the ballpark. And the point is actually, in a way, that we have other data, like the gravity data, that we can use to constrain it. So this is in the ballpark. It suggests that there's maybe something that you could do to try and separate out the thermal and compositional components of the signal that we see. But strictly speaking, the isopicnic hypothesis says that at every depth within the mantle, you have to balance whatever your thermal perturbation is with the right amount of compositional perturbation.
Yeah.
Because the velocity structure changes with depth, that thermal contribution must be changing with depth, and therefore you would have to be changing the compositional contribution. And if, in fact, you're not getting less depleted with depth as you're getting less cold, then that can't work at every depth. So
yeah, and also because the cooling history of our Earth, so even though it was isopicnic before and then
That's right.
cooling. So it's
Yeah,
not possible.
right. So that's another interesting point is that if you, let's say that it was perfectly balanced right now, that sort of means it can't have been in the past, right?
Yeah, yeah.
And that it can't be in the
Yeah.
future because you're not extracting more iron. So.
I was just going to say, just as a point of clarification, you always have to do this relative to some reference
Yep.
column, which is usually
That's right.
the oceanic ridge. I understand what you mean by you can't do it literally. I think the better word is strict isopicnic
Yeah.
versus isopicnic on average.
Right.
You do the average over the column. And I think that's
Right.
the point
Right.
you're bringing up.
Right. No, I mean, I think
That's
that's exactly right. Is that strictly speaking, you can't do this at every level and have it work out. It doesn't mean that there's not something along these lines that works, and hopefully we'll get a chance to talk about what those options are. So, this is mostly just to point out the issue. Yeah.
I mean, you can have a zero failure gravity anomaly.
Yep.
Even without isopicnic conditions.
Sure. Absolutely. This is one way to do it. You can get the zero anomaly, but you have to be able to get it. You can't do something that doesn't.
If it were isopicnic or neutral density, if the thermostat Earth is changing, what could also happen is that you have isostatic adjustments, and that can also end up giving you a free air.
Right. So in this case, the way that I did this, yeah, that's right. In this particular case, that's actually already accounted for, the way this calculation is done, because it takes into account the actual surface, the actual density surfaces. So that's an additional. I think it might address part of it, but I don't think it addresses all of it, actually.
Well, we could also bring in the people who talk about weathering. I mean, if that's the case, right, then you would see some.
Just follow up on this point. I mean, you showed us free air gravity. So if you don't have this strict aspect sort of model that is somewhere sort of overall there's a column balance, and then the geo actually will be a good thing to look at, right? Because geo is sensitive to the moment. So anyone
well, you got to pull out the glacial problem.
Well,
No. Right. Yeah. Actually, so I think there are a couple different approaches, right? And if you're going to do a flow calculation in the mantle, then you have to be very careful about that. But actually, this thing is a completely static calculation, which means that all of the configuration of the density is actually accounted for. So whatever the configuration is, it is, and you're making the gravity calculation from that. So there are a couple different ways to approach it. But here, you're not going to get out of the time variation problem by isostatic adjustment. So.
Can I?
Wait.
Can I make my point?
Since I made everybody sit in the first few rows, I want to know if someone in the first few rows, please come up with a question to ask.
I haven't finished, sorry.
I know, but you already asked 2 questions.
I haven't made my point. It's just because it's quite related to my research. Because through my PhD, I'm trying to figure out how the craton has been stabilized and stays such a long time with its thick lithosphere. So what I've figured out is that once the craton is stabilized, and because of the high viscosity, actually you don't. The strict isopicnic status is not necessary. So once it's stabilized, it's not necessary from my geodynamic modeling. Yeah.
Good. Okay. That's
the first point.
Yeah, I think there are a number of ways to get out of this, and hopefully we're going to talk about some of those. Okay. Did you think of a question?
I also was wondering if I could put a theoretical spin on this. I was wondering, you earlier in the talk had talked about increasing the resolution of the data for these global models to like 1 degree latitude by 1 degree longitude. But what about looking at paleotectonic reconstructions and looking at, because today we have pretty big continental dispersal, but what about supercontinents? And if you potentially would have a bigger differentiation in terms of higher velocities versus lower velocities under supercontinents versus bigger ocean basins?
What would the velocity structure look like when we have a supercontinent? Is that kind of the question?
Not sure.
That would be interesting to know, but I can't think of how to measure it. So if we wait a long time, I guess, it'd be interesting to know. Right, it'd be interesting to know how these distributions have changed over time. And I guess, unfortunately, a limitation is that we're taking a snapshot right now. But I think it does kind of come back to the question Roberto raised about if the crust is, the cratonic crust is sitting on top of cratonic mantle, may have something to do with the mantle and allowing the crust to sit there instead of the crust being extracted from that mantle, then maybe it means that things did look different in the past, and that was not elegantly expressed, but
I guess one answer is that, the kinds of models that I think Adrian will be talking about are very much, in terms of the geodynamics that include the long-term supercontinental dispersal assembly, are very much informed by the seismic results, because we think that all continents are sort of mutually buoyant and strong because of ecological effects. So what we take at the present day from seismology is very important for how we think about the things that work.
I think there is already evidence from seismology, at least in the North American continent, that the craton and its adjacent regions are formed from pieces or actually blocks, right? That have collided and then separated. I think you can see this in seismology various arrays.
Right, so we may actually be able to do a much better job connecting what's seen on the surface to what's underneath it as that resolution improves, which would be nice because, in some of, like some of the models I showed here, okay, you can see that cratonic root, but it really doesn't look like the blocks that are at the surface. So I think that's going to be one way to address some of these other questions as the resolution improves.
Okay. Oh, all right. One last question.
What about the variations in the two parameters, 0.84, 0.16?
Oh, right. I should not leave this up here because this was really... that's what... Okay, so, yeah, I mean, so that's what comes out of saying, here is... here's an assumption that we make about how these things are balanced out. Do something I think is sensible with the scaling, and make that isopicnic assumption. That's what you happen to get there. Don't take that as like don't write that down somewhere. This is kind of a back of the envelope. Does this even get you in the ballpark? Kind of a calculation. The answer from that is yes. It gets you in the ballpark with something like 85% of it coming from a thermal and 15% from compositional, but it must vary, right? Right. Yeah, exactly. And you would expect certainly that there could be variations in that ratio and other ways to do this. So it really is an argument to say this gets you in the ballpark of being able to explain in a reasonable way the seismic observations and be consistent with gravity observations. So it's really more just to raise this kind of discussion than to say this is what the answer is.
All right, lunch. So we may have all